everyone, and welcome to the 81st session of the Porous Media Tea Time Talks. I'm here today with my co-presenter, Brolo Santos, and we have two excellent speakers for you today, Yevgeniy and Mohammad. And we're going to get started straight away so we don't waste any time. And so our first speaker of today's session is Yevgeniy, and he is a PhD candidate in the Hildebrand Department of Petroleum and Geoscience Engineering, working under the supervisors of Professor Masha Brodanovic and David DiCarlo. Prior to pursuing his doctoral studies, he earned a Master's of Science degree from King Fahd University of Petroleum and Minerals. His research interests include hydraulic fracturing and foam flow in porous and fractured media, and he has contributed to these fields through multiple journal publications, conference papers, and patented innovations. And so I shall hand the floor over.
Thank you very much for the introduction, Catherine. So today I'm going to present my work titled Linking Foam Rheology to the Diversion Performance in Layered Sandbags under High Temperature and High Pressure Conditions. So I have been already introduced, but I just wanted to add that in my free time, I'm exploring some 3D modeling and some 3D printing techniques. And actually, I'm a merge designer for Digital Porous Media Portal. And this portal was founded by my advisor, Dr. Masha Brodanovic. And on this portal, every researcher can publish their data set. And currently, we do have some promotion that whoever publishes their digital research, we provide some gifts. And you can learn about this portal and the gifts that we are giving by scanning this QR code. However, my today's presentation is going to be about something else. It's going to be about foam flow in the porous media. And this is the short agenda of my today's presentation. I'm going to introduce the problem, explain the motivation behind doing this research. I will show you the materials and the methods that I used. I will demonstrate my experimental procedure, and then we're going to discuss some of the results that I got while studying the foam. So let's start with the short introduction. Foams are very well known in enhanced flow recovery. They offer significant advantage over just plain gas injection into subsurface because the gas is very mobile and it can quickly break through and appear at the production well. However, if we use foam, then we can significantly reduce the mobility of the gas and provide the uniform injection into subsurface. And at the same time, foam has an ability to plug high permeability zones and divert the flow into low permeability zones. And by doing this, we can improve overall sweep efficiency of the reservoir. So today, I'm going to talk a lot about the diversion performance of the foam. And actually, the question is, what is the foam? So the foam can be described as dispersion of the gas in the liquid stabilized by surfactant. So there has been a lot of research done to understand how the foam flows in heterogeneous or layered formations. And on this slide, I'm trying to summarize most of that relevant research. I can summarize that most of the research that was done in this area was actually focusing on visualization of the foam diversion. So most of the experimental work was focused on flowing the foam through layered formation and observing how the foam first flows through the high permeability zone and then diverts to the low permeability zone and then produces the fluid from both layers. However, researchers haven't tried to understand what actually happens to the rheology of the foam while it flows through that layered formation. And the question is, so let's say if the foam flows through layered formation, how its rheology different from the foam that flows through one of the homogeneous layers, and so on and so forth. Latest research that was published in 2025 actually tried really to understand at the micro scale what happens to the foam. And some researchers observed that when the foam flows through the layered formation, then it's a significant portion, especially the gas fraction, becomes trapped by that heterogeneity. And other researchers actually connected this amount of the trapped gas to the viscosity of the foam, and they observed that the more gas becomes trapped in the porous media, then it actually increases the viscosity of the foam. So it seems that the flow of the foam through the heterogeneous media is a very complex process, and that motivates us to study it in details. And also, as I said, most of the research was done at low temperature and low pressure conditions and at the micromodel scale, so that motivates us to expand this research further to a larger scale. And in my case, I'm doing experiments at a core scale. So, and also at some high temperature and pressure conditions that we can typically observe in the reservoir. So for this specific work, we had basically two hypotheses or two objectives. So first of all, we wanted to quantify the impact of the high temperature on the diversion capabilities of carbon dioxide foam. So essentially, we wanted to study whether the rheology will be affected or in general, the diversion performance of the foam. And then the second objective for this research was based on the question. So if the foam flows through heterogeneous formation, layered formation, and we record its certain rheology, and then we also flow the same foam through the homogeneous formation, basically one of the layers that constituted that layered formation, how the rheology will be changed. By looking just at the rheology of the foam, can we say that there was diversion happening or the structure of the foam was different? So that was the main question, and that was the second objective for the research. So let's talk about some experimental materials that I had. So all my experiments were done in the sandbag, and actually I had three sandbag configurations, and those you can see on the slide. So my first sandbag was layered, and the remaining two were homogeneous, and each homogeneous sandbag that I had was designed out of, so one sandbag was designed with 110 mesh size sand, and the second one out of 50 to 70 mesh size sand. And for the bilateral sandbag, I used the same sand sizes, but I positioned them in the layers. Also, a few words about my foaming solution. In order to prepare that solution, I was mixing 1 weight percent surfactant, and in my case, I used STO CS 330 surfactant with 5 weight percent sodium chloride brine. So this is my experimental setup that I used for all of my experiments. I know it looks a bit complicated. However, the essential idea behind this setup is that I can inject simultaneously CO2 gas and surfactant solution and generate the foam. And it's important to mention that in my experiments, I was always pre-generating the foam by injecting CO2 and surfactant into small sandbag that was located before the actual sandbag where I was conducting all the measurements. So the reason I was doing that is to ensure that from experiment to experiment, I generate the consistent foam, and then all the changes to the foam that can happen inside the actual sandbag where I take all these measurements. So in my experiments, I was measuring the differential pressure, and then I knew my flow rate, permeability, and dimensions of the sandbag, so I could just back calculate for the viscosity and assess the rheology of the foam. So this is a table that contains information about all my experiments. I did them at 3 different temperatures and 3 different flow rates. And in each experiment, I varied foam quality from 65 to 99%. And it's also important to mention that I kept 1200 PSI of the back pressure in all of my experiments. So this slide was designed for you to understand how the typical experiment looked like in my case. So in every experiment, I recorded the differential pressure across the sandbag and while continuously injecting the foam. So I would start my injection at very small foam quality of 65%, and then increasing it stepwise by 5%. And then during each step, I was waiting until the foam is stabilized, and I see a steady state, record that pressure drop, and then use it in the back calculations for the viscosity. And now let's talk about some results. So these are results of the petrophysical measurements. So I assessed the permeability of the sandbag prior to each foam injection, so that I can use that permeability values in the back calculation for the viscosity. So in this case, the smallest permeability, actually it's too high, but in my case, it was the smallest permeability that I observed was for 110 mesh size sandbag. So, and it's something that someone would expect, because this sandbag had the smallest size sand particles. Then the highest permeability we achieved was for 50 to 70 mesh homogeneous sandbag. That was around 28 Darcy. And then, as expected, the bilateral sandbag was somewhere in between, because it was the arithmetic average of both of the sand layers, and its permeability was around 23 Darcy. So let's talk about results of the foam experiments. And on this slide, you can see a combined figure that contains all the rheological curves that I obtained during my 27 experiments for 3 sandbags, and you can see them color-coded. And let's talk about this figure one by one, and we'll start with the impact of the temperature. So in all of our experiments, we consistently noticed that the foam that we generated at 90 degrees Celsius and 120 degrees Celsius was similar in terms of rheology, and the viscosity was the same. And that's something interesting to explore further. And we also observed that at 150 degrees Celsius, the viscosity of the foam decreases significantly, and that difference between rheology is especially high for the high foam qualities. We did further analysis, and in this case, we fixed the foam quality and just constantly injected it into the sandbag while varying the temperature over time. And we observed some interesting results. So someone would expect that at low temperature, actually the foam might perform better. However, that was not the case for us. There was some optimum temperature that we observed, and it was around 100 to 110 degrees Celsius, after which the viscosity of the foam decreases, and then eventually the foam collapses at 180 degrees Celsius. And you can notice that this peak is especially observable at higher foam quality. So let's talk about the remaining results. Also, during all of our experiments, we consistently noticed that the rheology of the foam that was generated in the layered or heterogeneous sandbag was stronger. It means that viscosity was higher for this foam compared to the foam that we generated in each of the homogeneous sandbag. And what's more interesting is that the rheology of the foam in the heterogeneous sandbag was closely comparable to the viscosity of the foam in the low permeability layer. So that can tell us something about the behavior of the foam in the layered sandbag. And we can logically propose that in all of our cases, the foam was diverting and flowing through the low permeability layer, and that low permeability layer was the one actually affecting the rheology of the foam. Because if there was not a diversion, then we assume that the rheology of the foam would be more similar to the rheology that we obtained in the high permeability homogeneous sandbag. And it's also important to mention that once we increase the flow rate and increase the temperature, that difference actually becomes negligible. So that means that for the actual field operations, it's very important to properly select the surfactant based on the final temperature, or actually target temperature of the reservoir, and at the same time the injection rate, so that we can maximize the performance of the foam during enhanced oil recovery. So these were the key findings. And just to conclude, we in our experiments we observed something other researchers would observe in their experiments, but at a smaller scale. So in our heterogeneous setup, probably also some portion of the gas of the foam would be trapped, and that overall caused the increase in the viscosity of the foam, and also that complex heterogeneous system would better mix the foam, and then the overall rheology would be better. And also we observed that there is some optimum temperature for the surfactant that we were using, and that's something other researchers also observed for their surfactants as well. So the research that I was presenting was published as part of the journal in Energy and Fuels, and also presented during the conference. And here I'm providing those references that you can go through if you are interested in this work. And you can ask me the questions by mailing me at the email that you can see on the slide. And that's all from my side. Thank you very much for your attention, and I'm ready for your questions.
Great. Well, thank you so much. That was a really interesting presentation. So if people have any questions, please leave a comment and we can ask them, and we can read them out to the speaker, but I will get started. So I was wondering, basically with the pressure profile that you have across the core, did you quantify like the magnitude of the fluctuations about the mean? And can you relate that to any of the dynamics that you saw within the experiments?
Thank you very much. That's an excellent question. And from this profile, you can see that once we increase the foam quality, which means we introduce more gas, then those fluctuations become more aggressive. So I wouldn't say we actually quantify those fluctuations, but in general, we would record that pressure drop over the time, and then take the average pressure. For sure, for the higher foam quality, it becomes less accurate, but this is the maximum that we can do, because that's the typical behavior that you would expect when there is a lot of gas in the system. And you can also see on that picture that you really have those slugs of the gas flowing through the system, and that affects the pressure drop readings that you have.
Yeah, I would be interested to see if like the magnitude of the fluctuations could be correlated to maybe the amount of like dynamics that happen from the foam or the gas in the porous medium. I'm wondering as well, like, can you from these experiments determine how much of the foam channels through, say, the high perm region? Like, do you think it's full channelization, or do you think it's like majority in the high perm region? Is this something that you were able to quantify?
So our quantification is basically limited to that rheological curves that we have, because it's a high temperature and high pressure environment, and we cannot have more visualization rather than just those pressure measurements. But from the consistency of the experiments, we continuously see that the foam that we generated in that layered formation was like more viscous. So that tells us something, that something different is happening in that specific setup. And we were trying to refer to what's happening through the literature that I was showing, and we observed those some consistencies. So I guess the main idea is that the foam flows through that high permeability region, and then at some point it diverts, and then this diversion helps to change the structure of the foam at a micro scale, and then this further helps to achieve the higher viscosity.
Very interesting. Yeah, I would be interested to see if, like, in the pressure itself, like if you look at the spectral signature of the pressure, if you can see it going into the smaller pores of the lower permeability region. I think that that would be something to look at. But
Yeah,
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 very interesting work.
that's very important as well, because it might be also one of the indicators of, movement of the foam in the subsurface. So because it's a big question to understand when you inject the foam where it goes actually. So then by monitoring the pressure, you can really understand where it goes through the layers, and that's what we were trying to observe in our experiment.
Great. Well, thank you so much. That was really interesting. I'm going to hand over now to Brillo. Great. Let me.
Yeah, thank you once again. And I'll have some questions through the email to the last speaker. So going further, our next speaker is Mohammad Salehpour. He's going to present his work, phosphor ripening and underground gas storage. So a brief description for his work. Mohammad Salehpour is a PhD candidate in civil engineer at Master University under the supervision of Dr. Bengzong Zhao. His research focused on the pore-scale physics of fluid flow in porous media, combining microfluidic experiments and theoretical analysis to investigate processes relevant to underground gas storage. So please, Mohammad, the floor is yours. Thank you once again for the availability to talk to us today.
Thank you, Berlo, for the introduction. Hello, everyone. My name is Mohammad Salehpour. I'm a PhD candidate at McMaster University under the supervision of Dr. Robin Zhao. Today, I'll be presenting some of our most recent results on oswald ripening in underground gas storage. So underground gas storage has strong potential to play a pivotal role in the energy transition. For example, CO2 sequestration. For geological CO2 sequestration, CO2 is captured from different emission sources, compressed and injected into deep geological formations for permanent storage. One of these geological formations is deep saline aquifers. They are layers of porous rock filled with brine. They're large and widespread, and they have low economic value. Similar to CO2 sequestration, hydrogen can also be stored under the ground. Hydrogen is great for buffering the intermittency of renewable energy sources. For example, during the seasons that the demand is lower than the supply, the energy can be converted into hydrogen and stored in geological formations. And then during the seasons that the demand is higher, this hydrogen can be extracted and then converted back into energy or electricity and be used. During underground gas storage, residual trapping is a frequent phenomena that can happen. So when gas already exists in the porous media that was introduced through drainage, when imbibition starts, water is pushing the gas out, the residual gas can get trapped inside the porous media. It can follow several mechanisms. One of them is bypass trapping, which the wetting phase flows around the region of non-wetting phase and traps the bubble inside the porous media. Another one can also be snap-off, where the wetting phase invades and swells in narrow pore throats. And similar to CO2 sequestration, during cyclic injection and withdrawal of hydrogen, same thing can happen. We can have residual trapping of gas, as we can see in the below figure, where after imbibition, there are isolated ganglia trapped in the porous media. So before we talk more about the trapping, let's quickly discuss oswald ripening. Oswald ripening is a curvature-driven mass transfer process. In an open system, like shown in the below figures, where there is no confinement on the bubbles, a population of many small bubbles have a large surface area or interfacial area, which translates to higher interfacial free energy, compared to when we have fewer larger bubbles that have smaller interfacial energy. Oswald ripening or coarsening reduces the free energy in the system. And the mechanism is very interesting. Smaller circles, smaller bubbles have smaller radius and higher internal pressure. And this higher internal pressure causes the gas to diffuse into the surrounding water and diffuse back into larger bubbles. And over time, we can see that small bubbles disappear and larger bubbles get larger and larger over time. So does this happen in porous media? Absolutely. But there's a big difference in oswald ripening happening in a porous media and in an open system. In porous media, we have confinement, and the size of the bubbles do not correlate necessarily with their radius of curvature or their internal pressure, as the interfacial curvature is dictated by the pore geometry rather than the bubble size alone. And from the microcity experiments, we also saw that oswald ripening can happen over time scale of hours. Again, from the figures below, we can see that after imbibition, after 12 hours, we can see like some changes in the size and shape of the bubbles, which is also which can happen in other experiments that is shown after imbibition. After 16 hours, we can have changes in the size of the bubble and their shapes. So we currently know that oswald ripening can happen in porous media, and it can take multiple hours to reach that. But there are some open questions in this field. Do bubble sizes govern the ripening dynamics? What is the collective ripening dynamics of bubble in realistic pore geometries rather than a simplified system? And what is the long-term behavior of ripening? In order to answer these questions, we came up with a microfluidic study. We investigate the dynamic of hydrogen ripening using several experiments. Our microfluidic enables us to track the trapped hydrogen bubbles across the entire domain rather than isolated pores. It provides direct visualization of fluid-fluid interface at pore scale. And each experiment can last over 2 weeks, depending on the temperature that it was performed at. Our microfluidic is shown in the figure below. This pattern is derived from a segmented image of a natural Canadian sandstone, preserving its pore scale heterogeneity. It is fabricated through DRIE process at a uniform depth of 7.8 microns, and then bonded to a borosilicate glass. A heating element is positioned under this microfluidic to enable us perform experiments at high temperature. And this microfluidic measures 10.19 millimeter by 4.25. And a characteristic of this microfluidic is the channels that are at the inlet and outlet, which have the sizes or the widths of 140 micron and 100 micron, which are larger than the median pore size of this microfluidic, which is about 40 micron, and the median pore throat size about 10 micrometer. So in order to obtain high resolution images of this microfluidic, we use an XY motorized stage. We program the stage in a way that it moves in a serpentine pattern and obtain images for 15 columns and 8 rows. So in total, we capture 120 images with specific overlap between them. And at the end, we stitch all these images together to get a really high resolution image with a pixel size of 0.31 micrometer per pixel. So after performing the experiments, after fully saturating the microfluidic with water, performing drainage and an imbibition cycle, we saw that we have trapping of hydrogen inside the system. In this figure, we can see that these trapped hydrogen can have various shapes and sizes. We can have bubbles that are trapped in one pore and bubbles that expand through several pores. An interesting feature of these bubbles is that the hydrogen-water interface of each individual bubble exhibits uniform in-plane curvature, which shows that each bubble is at local equilibrium. However, this curvature, the in-plane curvature, can be different between each discrete bubble in the system. And most importantly, we saw that there is no clear correlation between the radius of curvature of the trapped bubbles and also the area of the trapped bubbles. So we examined the pore scale behavior of the trapped bubble near the center of microfluidic. Here we are looking at the video that is that's taken over 15 days with higher temporal resolution in the beginning and less frequent images after a while. After the first 5 hours, we can see that neighboring bubbles rapidly reach local equilibrium. Some bubbles start shrinking, some bubbles start losing gas, and with minimal changes in their volumes, they reach a metastable configuration. However, after a period of 15 days, all of these bubbles collectively start losing gas. That's where the effect of boundaries is felt in the middle of the microfluidic, and all the bubbles start depleting into those boundaries or sinks. So to quantitate this observation, we pick an area, a field of view in the middle of the microfluidic, distant from both right and left boundaries, and we look at the gas saturation and the radius of curvature, and also the standard deviation of radius of curvature of the trap bubble in that specific field of view. We can see that during the first 5 hours, the changes in saturation and also the average radius of curvature is minimal. However, the standard deviation reaches its minimum value, which shows that bubbles are reaching local equilibrium and their radii of curvature is similar between the ones that are trapped in this field of view. However, after the first 5 hours, we get to stage 2, where all the bubbles start losing gas. The average radius of curvature starts increasing because the bubbles are receding from the throats and their radius of curvature increases, and the gas saturation drops in this specific field of view. A similar trend is observed for the whole domain, the whole microfluidic. However, distinction between stage 1 and stage 2 becomes a little bit more complicated because from the very beginning, we can have gas loss from the boundaries, from the area close to the boundaries to the boundaries. But the collective behavior is very similar to what we saw in the previous stage. And these 4 experiments are at 2 different temperatures and 2 different initial saturations. So we develop a continuum model for asphalt ripening in porous media. This model is shows a spatial-temporal evolution of the fraction of dissolved gas in aqueous phase. After applying low gas solubility and density assumption, we can reach to a more general format of diffusion equation, with the effective diffusion defined as the function that's seen in here, which is a function of the diffusivity constant of the gas in water, Henry's constant, molar densities of gas and water, and the slope of PCS curve. So in order to connect our pore scale observations to microscopic diffusion, we use PCS curve. This PCS curve is obtained through a method referred to as pore morphology method, which after taking an image of the porous media, running this algorithm on it, we're able to extract the PCS curve. And using this model for our experimental conditions, we can see that the model predicts the experimental observation really well without any tuning parameters. And using the characteristic time and normalizing the X and Y axis, can see that all the experimental results collapse, which is a great sign. So we have performed some experiments. We have done some modeling. We have gotten great results. But what kind of insights can this give us for large-scale prediction? As we showed, asphalt ripening is driven by gradients in capillary pressure, which are governed by the spatial distribution of saturation. So in order to answer this question of what happens at larger scale and how we can use our understanding, we applied the PMM code to extract the PCS relationship from several different 3D images from microCD for different sandstones. And using Henry's law and also Chain's rule, we were able to write the diffusion equation based on saturation. We also analyzed existing core flight experiments and found that the residual gas saturation varies between millimeter to centimeter scale, which is far exceeding the characteristic pore size of tens of micrometer. So the question here is that how long does it take for asphalt ripening to erase these spatial variations of saturation that we see in the system? So after extracting all these 1D saturation from the literature, we're able to fit sinusoidal curves to these. From these curves, we can extract the average saturation, the amplitude, and also the wave number, the wavelength. Using these information as initial condition, we can solve the diffusion equation analytically and obtain an equation for local equilibrium time, which this function depends on the wavelength of saturation variation, which I showed in the previous slide, and also the effective diffusion, which depends on petrophysical characteristics of different gases. So we go and obtain all these information, the physical properties of different gases for hydrogen, CO2, and methane at different temperatures and also different depths. And using these, we're able to solve the T equilibrium equation and obtain a figure for showing the local equilibrium time for the stored gas under the ground versus depth. Here at depth of 1 kilometer, we're showing that the equilibration time for CO2 has a median value of approximately 300 days, which is a lot shorter than the typical onset of convective dissolution, which is 10 to 100 years. And also this equilibrium time for H2 is about 700 days, which is in the same order of magnitude of 6 to 12 months of injection and withdrawal cycle. To summarize our results, we've developed a microfluidic platform to investigate long-term hydrogen ripening behavior. We've also been tracking the trapped hydrogen bubble inside the porous media, and we saw that they rapidly reach local equilibrium followed by slow global depletion by long-range diffusion to the boundaries. We developed a continuum model that closely reproduces the experimentally observed data without any tuning parameter. And also the reservoir relevant estimates showed that the local equilibrium far outpaces the convective dissolution of CO2 and occurs at timescales comparable to seasonal H2 storage. Here we showed that the minimal redistribution is required to reach local equilibrium and to remain stable in the absence of sinks. And yeah, that wraps up this presentation. Thank you very much for your time. If you are interested in knowing more about asphalt ripening and more specifically our research, please scan this QR code. And if you have any questions, please feel free to send me an email. Thank you very much.
Thank you very much, Mohammad, for the very nice talk. Very interesting and very nice how the work is very complete with experiments and also mathematical modeling. We're still waiting if we have some questions from the chat, but I have more technical question before because you did some experiments in the micromodel, and I think it's very common to have some challenges with the stability of the chip, since you have usually you have a box with a device to control the temperature and the chip inside. So there could be a lot of vibrations. Did you have this kind of challenge? And if you did, how could you treat the images so you could have it well parameterized with this fine resolution that you had?
Yeah, that is a great question. It was one of the challenges early in the experiments. So when I started the experiments at this resolution, we also noticed vibration even when someone was walking around the setup. So we were lucky enough to have 2 labs. One of the labs is in the basement of a building, and it's the floor is concrete. So we moved the setup there, and we made sure that there's no vibration in the experiment. So we kind of used that lab to eliminate the vibration in the system. Yeah.
Nice, very nice. And you showed the slide with the oscillation comparing nitrogen and CO2. This is directly related to the dissolution of the gases that is different, or it would be any other reason related to it?
Sorry, let me go back to this. Are you referring to this slide?
Yes.
Yeah, so these are the 1D saturation of trapped gas in core plugs that we gathered from the literature. Yeah. So I'm not sure if I answered the question or not.
Yeah, no, because I noticed that the oscillation rate is different for both of them. I was just wanted to be sure that I understood, because at first sight, my impression is that these different frequencies is because the dissolution of the gases are different in water.
Oh, I think these images are taken at early in the experiments. So these are from microcity images, and these are the residually trapped gas in the porous media.
Okay.
Yeah, that are not dissolved in the aqueous phase. Yes. Yeah.
Okay. So thank you.
Yeah.
May I ask a question as well?
Yeah, of course.
I was wondering if you were able to link like the rate of dissolution or any of the 2 stages to the connectivity of the pore space in those regions.
Yeah, I think using the PMM code, we are able to extract the correlation between the saturation of the trap gas, the saturation and also the capillary pressure. So this capillary pressure is based on the heterogeneity of this porous media, which is how well the pores are connected to each other, how long the throats are, and all of that. So I think that is kind of incorporated into the 1D model that we developed, that it looks at how pores are distributed, what the heterogeneity of the system is. Yeah.
Interesting. Great. Thank you.
Thanks.
All right, so I think we will finish the session. Want to thank once again our both speakers and Catherine to taking the lead. It was a very, very great session. So want to say to the audience to stay tuned to our network, our YouTube channel. We'll very shortly will share the details for the August session. And I think that's it. I'm missing something, Catherine?
No, that's great. Thank you so much to our speakers.
Okay, so
And yeah, great.
Okay. Thank you.
Thank you very much
you guys.
for